So let us go with a first example that we can do with algebra of limit. Example an is equal to, for instance, some n cube plus 6 n square plus pi n minus 2, and here we have, for instance, 7 n cube plus e n plus 5. And so what happens to the limit of the sequence? So there are various ways to do that. The simplest way is to collect the highest degree power at the numerator and denominator. So in numerator, so we end up with 1 plus 6 over n plus pi divided by n squared minus 2 divided n cube. And here we have n cube, and we end up with 7 plus e over n squared plus 5 divided n cube. So what we have here is that we know that 1 over n goes to 0, so 6 over n goes to 0 because it is 6, a constant, times 1 over n. And so applying the theorem on the limit of a sequence made of a convergent sequence by a constant, then here we end up with the same limit, the constant by the same limit. The same here, pi over n squared, 1 over n squared goes to 0, multiplied by pi is 0, and so on, and so on, and so on. N cube and n cube up and down cancel each other, so we end up with 1 over 7. So this is a general procedure. Probably you already know this procedure, but so generalizing, we find that P of n given P of n, Q of n, two polynomials polynomials of the same degree we have that the ratio sequence an is equal of P of n divided by Q of n, that we can write that like a highest degree term CD times ND plus C D minus 1 n to the power D minus 1 plus dots plus C1 n plus C naught. And here we have other coefficients, for instance, k d n d plus k d minus 1 n d minus 1 plus dots plus k1 n plus k naught. So we act like in the explicit example. So we collect out the highest degree power from numerator and denominator, and then we end up with CD plus CD minus 1 n to the power minus 1 plus many dots plus C1 n to the power n1 minus d plus C naught n to the power minus d. The same thing holds for the denominator. So here we have kd plus kd minus 1 n to the minus 1 plus dots plus k1 n 1 minus d plus k naught n to the minus d. So this here everything cancels out, and the result, the final result is CD over KD. Okay, this is the case in which you have to deal with a ratio of two polynomials of the same degree, but there is another case. This was the first case. A second case that we can already treat is when the degree of the numerator p is less than the degree of the denominator q. Then the conclusion is that the ratio of p and q converges to 0. Let me give you just an example. If we consider n plus 3 divided n squared plus 5n minus 1, for instance. So here again, gather out the highest power terms of numerator and denominator, and so you collect out n from the numerator, and here you have 1 plus 3 over n. You collect n squared out of the denominator, and here you have 1 plus 5 over n minus 1 over n squared. So we can reason exactly in the same way as before. So here we have that this goes to 0 and this guy goes to 0, goes to 0. So by using the whole algebra of limit, I don't want to detail every step, but by using the algebra of limit, at the end you have that this ratio goes to 1, and here you have n over n squared, and this is 1 over n, and this goes to 0. And of course, this method can be applied to the general case, when you have the ratio of two polynomials in which the degree of the denominator is strictly higher than the degree of the numerator. And now let me go to the other case, but before I give you just a definition, not an important definition, just a name, but when a sequence an converges to 0, then it is called an infinitesimal. It's just a word. Don't try to search for some philosophical meaning. To our concern, it is just a word. Okay? And then there is another case, the last case, in which the degree of the numerator is strictly higher than the degree of the denominator. And so, as an example, you have an is equal to 2n cubed plus e. I like these numbers like e and so on. And here we have 5n squared plus n plus 4. So let us try to apply the same strategy as before. So here we collect n cubed, and here we collect n squared. So here you have 2 plus e over n cubed, and here you have 5 plus 1 over n plus 4 over n squared. So this goes to 0, this goes to 0, this goes to 0. So this ratio, by applying, as usual, the algebra of limits, this ratio goes to 2 over 5, 2/5. Whereas the two highest power terms give n. Now, here again there is the product of two sequences, one sequence that goes to 2 over 5 and another sequence that is equal to n, but n is not convergent, so we cannot apply the algebra we know. Okay. And how can we prove that it's not convergent? So it is quite obvious, but let us find that simple method and quite instructive. So it is a remark. If an is a convergent sequence, then for every epsilon larger than 0, there exists an n bar that depends on epsilon such that for every couple of indexes n m larger than n bar, we have that an minus am is less than epsilon. So this definition, so a sequence that fulfills this rule asterisk is said a Cauchy sequence. And so what we proved, okay, proof of this remark, the proof is very easy. So let epsilon be larger than 0. So there exists some n bar such that if n is larger than n bar, then an minus L, so L is the usual the symbol of the limit, am minus L is less than epsilon over 2. Okay, we use again epsilon over 2. Now we consider two numbers n and m both larger than n bar, so we have that an minus am, we subtract and add the limit L. We use the first triangular inequality, so here we end up with an minus L plus L minus am. For both n and m, since they are larger than m bar, this inequality holds, so here we have epsilon over 2 plus epsilon over 2, and this is epsilon. Okay, and so another remark is the following. It says, we proved that convergent implies Cauchy. The contrary is also true. but difficult to prove. Okay, so I don't leave it as an exercise for you. You know that it is like that, but okay. And, I don't really, I will not ask you the proof of that. I will not do such a proof. And basically, the statement is that convergent is equivalent to Cauchy. Convergent implies Cauchy, Cauchy implies convergent. But we will use this Cauchy characterization in order to prove that something is not convergent. For instance, as an exercise, prove that an equal to n is not convergent. And this is quite simple. Let epsilon equal to 1/2, for instance, or whatever you want. So, and for every n, if you have a n plus 1 minus a n, this is n plus 1 minus n, minus 1, minus n, sorry, and this is equal to 1, which is larger than 1/2. So, an is not Cauchy, and then not convergent. Basically, the idea of a Cauchy sequence is that sooner or later, the elements of the sequence tend to focus, to concentrate, one near to the other. So, and it is clear that if the sequence is convergent, since elements of the sequence eventually accumulates around the limit, it is clear that they accumulate among themselves too. It is not so easy to prove the contrary. So if they accumulate exactly in the sense of this definition, then the sequence is convergent. But it is true. Okay. So, and of course, this phenomenon of accumulation of the elements of the sequence does not occur for an is equal to n. Let me give you another exercise. This is just for you. It is very simple. Prove. We already proved that, but I want you to prove using Cauchy sequence, using the definition of Cauchy sequence. That minus 1 to the nth power is not convergent. Now, we want to go back to an is equal to n, and we want to focus on this feature. The feature that is the following. So, a interesting and important feature of the sequence an equal to n is that, so I put here quotation marks, even though it is not a quotation, but it is important. Fixed an arbitrary number the sequence lies eventually at the right hand side of such number So what happens is that you are here, you fix some m, and at the beginning of the sequence, you here at the left-hand side. But at some point, it remains always beyond m. Then you fix another k here, and again, eventually, after some n bar, the sequence lies also beyond this k, and so on and so on. So this is the important feature I want to fix. And from the other point of view, the point of view of the graph of the function, eventually the sequence lies here, beyond a fixed m, then you fix another one, k, for instance, here, and eventually the sequence is beyond k2, okay? And this is the basis of the last topics of today's lecture, that will be divergent sequence, and I will come to divergent sequence with the next video.